Today we are going to look at unit number 2, lecture number 5. So here also in this class also we look at some basic gate level modeling, some important modelings that we will look at here. I think it is 4 or 3. I think it is 3. Yeah, it is 4, right? It is 3, I think. 3. Lecture number 5th actually. Okay, again we'll start. Just wait for a moment. Just you just turn on this projector. Turn on this projector. Here. Just switch on the fan and turn on the fan also. Okay, this is unit number 2, lecture number 5, and gate level modeling examples 4. Okay. Okay, fine. Okay, still projector has charts in it, right? You go and ask the person. Somebody will ask. I think it is already 1 minute. So please, all of you try to write a Verilog program for 2x1 multiplexer. Write a Verilog program. For 2x1 multiplexer. Just you have to use only buffers. In the last class, we have seen that we have used the basic gates, some like AND gate and OR gate we have used. Now our constraint is we have to use only the buffers. Okay. So as we know that operation of the 2x1 multiplexer, but realization is done or implementation is done by using the buffers, not AND OR gates. Okay. So screen రావట్లే. Okay, so this is what our the objective. We need to write a Verilog program for 2x1 multiplexer, but by using the buffers only. Okay, so as all of you know that what is the top level module for this one? The top level module is something like this. Having it look like a black box consisting of 2 input signals. Okay, Vector notation I'm interested to write. Okay. So in the vector notation, 2 input means I will consider it's a 2-bit size, and selection line is only one selection line. Y is my output line, right? Fine. Now, what is the inside of this black box? So many ways that we can model this one. So many ways we can design this one. One way is that by using the buffers only. Okay. So let us take the buffer circuitry for this one. So let us consider in this way. We are going to use one buffer here. Buffer means tri-state buffers are useful here. Tri-state buffers. Okay, I'm going to use a not buffer here. Okay, and I'm going to use here is another buffer. Okay, it is actually also considered in this way. So this is normally I of 0. Therefore, this is called I of 1. These two are connected here. I think the design I'm not going to tell you. So directly I'm telling all these things. So Y is my output. So if I put a selection line here, and the same selection line I'm also using for this one also. Okay, see if S is equal to 0, if S is equal to 0, what will happen? If S is equal to 0, the top buffer will be active, but bottom buffer will be high impedance state. Okay, therefore it becomes a high impedance state here. It becomes I of 0 will be the case. Okay, therefore since it is a high impedance state, means it does not have any connectivity to the output node. Okay, therefore Y is actually becomes I naught only. Okay, I becomes I naught, Y becomes I naught. Now later, if you use S is equal to, for example, S is equal to 1, okay, and here it becomes Z, here it becomes Z, but here it becomes I of 1. Therefore, Y is actually I of 1, right? So therefore, that's how we are going to implement our 2+1 multiplexer, okay? So therefore, at a time, only one signal will be selected as an output signal. Okay, this is acting as a multiplexer. Now we need to model this one with the help of Verilog language. Okay. Okay. So for simplicity, I'm removing all these things. I think operation you better you know all these things. Okay. For simplicity, I'm removing all these things. So this is what actually inside of your black box, right? We have only 4 signals outside of box. Okay, fine. So let us write quickly the modules. Let us write a module here. So what is the name of the module? For example, mux underscore 2+1 by using buffers. That's why buff I'm writing. Okay, we can use any name, no problem. So here I am considering the I is Y. Okay, what are the inputs here now? Inputs are 1 down to 0 of I. Am I right? So once the statement is completed, after the semicolon, the statement is completed. It is possible to write another statement here also. Another input we have that is called as. So I'll write output here. The output is actually Y, right? Y is my output. Fine. Now I'm going to write the modules. So what is the keyword that we have to use for the buffer? What is the keyword? Buff if 0, that is stands for G1. So this, let us consider this is called G1. So this gate is G1. This is called G1. This is called G2, for example. Okay. Yeah. Okay. The first G1 is actually buffer G0. So G1, sorry, G1 I have written, right? G1 only I'll write. G1. Okay. So what is the output for this one? Output for this G1 is Y. Y directly Y is connected to that one. Okay, Y directly connected to that one. Okay, therefore Y is my output. Okay, next what should I do? I need to write input signal, then control signal. That is what the syntax for the buffer. Okay, first we have to write the output, then input I need to write I of 0, and then I should write control line. That means selection line I need to write. So this is the syntax for this. Similarly, I will consider for another buffer. Buffer 1, here is the 1. For the 1 it is acting, right? Buffer 1, the gate is C2. Y is my output. I of 1 is my input. S is my selection line. Okay. Finally, we need to end the module. This is how we know already. Okay. But very important thing is that one point we have to remember. So whenever a tri-state gates are connected at one single point, okay, that means this is the point we are talking about. This is the tri-state output. We are tri-state output of the first gate, tri-state output of the second gate. We are connecting at the same point. Okay, so therefore here, for example, if it is a one logic one, for example, here is a logic one, here is a logic high impedance state. Then which one has to select it? Logic one has to select it, or logic or high impedance must be selected. So that is the question actually. Okay, so therefore, it is not good advice to consider the output Y as a wire data type. Okay, so default values for the input and outputs normally. So normally here we are writing, right? So you consider this one. So these things we are writing on normally. So what is the default value of this wire? Sorry, default value of the input is, see, if you take any line, in your design, that must handle some kind of data. That means it takes some kind of data, or it can send some kind of data through that particular net or a signal or a line. That line will take some kind of data, right? So that data must be any one of the type. It may be a net type, or it may be a variable data type. Okay. So default values for the net or default data type of a net is actually a, or I can say that in this way. So for example, as I mentioned in this way. So here is my input. Okay. Here is my output, right? For this particular gate, whatever it may be, it doesn't matter, whatever it may be. Okay. So the one line, this is called a line. This is called a line. This is also called a line. Okay. In Verilog point of view, this is called a net. Net. So this is also we will call it as net. It may be input net, it may be an output net. Okay. So the default value for the net. So what net has different type of types are there. Okay. So in this for this particular net, we use the data type called wide data type. Wide data type. So we have seen something about this one. Wide data type we have to use. Either this one also we need to consider as a wide data type. So other data types are also there for the signals. Okay. So these are called default values for the net. Okay. So therefore, even if you are not writing input is I is 1 down to 0 of I, default it is actually we need to write as a while actually. Okay. So how do I write like this one? So instead of saying like this, I need to write in this way. While 1 down to 0 of I. That is what actually the right notation. When you are writing the input declarations and output declarations, okay, unless otherwise you are not specifying it is a variable data type, it must be a net data type only. Okay. So therefore, net data type is nothing but one of the important net data type is while. What is the responsibility of the while? It takes the input and send the output, send it as an output. Okay, just it is a passing information, passing element only. That's all. So therefore, input will take the information. Output, if you are writing as a while, that is giving me as an output signal. Okay. So therefore, input is a wire, something like this we need to write. So therefore, default values of these inputs and outputs are actually wire data types. But whereas if you're using the tri-state buffers, the output must be represented by tri-type. Okay, therefore, another important data type is a tri-type. Tri-type. Okay, so therefore, this is also a tri-type. So normally we don't use the inputs as a tri-type, but outputs we are represented as tri-type. Okay, so uh, therefore, the better to consider here is output as a tri-type. Okay, try y I need to write. Try y I need to write. Okay, or otherwise output try y also we can write it there. Otherwise, output try y. So which means that that means we are going to connect the two tri-state buffers at a single point. That driving point must be represented by tri-type. Okay, therefore there won't be any kind of complexity in it. Okay, therefore immediately by writing the try is output is a try type. If it is logic 0, for example, here is a logic 1, it is a logic 0. So it won't take into consideration this line, this high impedance state or try state is not at all taken into consideration. Only the known value will be considered. So therefore, the I naught will be selected as an output signal. I naught will be selected as an output signal. For example, in the I1 state also, for example, it is there may be a possibility. Another one is this is Z, for example. This is Z, and here is I1 is Z. So which one will take? Since we have represented y as a tri-type, therefore tri-state information need not be considered. Okay, it will consider only the known value of the I0 only. So I1 only. Sorry, I1 here is I1. I1 only will be considered. Okay, therefore I1 only will be considered for that one. Okay, so that is the point that we have to remember when we are dealing with tri-state buffers. Okay, for the normal gates and all these things, we don't bother about it. But when we talk about the tri-state buffers, that too, when we are connecting at a single point, 2 or 3 tri-state gates are connected at a single point, then it is necessary to mention as a tri-state output. Okay, fine. So anyway, now let us write let us write the test bench for this one. Okay. So shall we write a test bench? What is the test bench? How do we write a test bench? The last class I told you that you have to complete the test bench. Now I'm going to write the test bench for you. You please go through it. So let us write a module. So test bench, I'll write a keep heading test bench. Module test underscore mux underscore 2x1 underscore buff. This is the name I'm giving. Okay, this is everything must be written in black color. This is because it's a user defined. Test underscore max underscore 2x1 underscore buff. There should not be any kind of space between that one. If you want to mention any kind of space, better to you have to write an underscores. Okay. Okay. Now next, the inputs are represented by register data type. Those are all 1 down to 0 of I. Okay. Another one is reg yes. Reg yes is also we will have to consider. And output is represented by wire type. Wire y. Then that's all. Next, we need to call the instance name. Okay, directly as it is name that we have to copy. Okay, this is the name exactly we have to write. Otherwise, it is not possible to test that one. Okay, whatever we are testing, that name must be required. Okay, so this is the one. We are treating this is the module. Okay, this is the module number 1, consisting of I first input, second input, y is my output, right? So irrespective of it is a buffer implementation or it may be a logic gate implementation, doesn't matter for the test bench. Okay, test bench is unique for every design. Okay, so that's what we have to remember. Now initial we have to write initial. Let us begin. See, so I have a test bench something like this. I have only inputs are only 2-bit size input of y, 1-bit size is s and y. Okay, I need to consider for this one. What are the inputs that I have to consider? First, I'm going to consider for s, then I'm going to consider for I1, then I'm going to consider for I0. That means altogether we have 3 signals are here. Okay, for these three signals, I need to mention its combinations. What are the combinations? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay, so 1, 1, 0, 1, 1, 1. That means this information I need to place it here. Okay. I want to place all these things in this way. Okay. So what is the best way that I can do? So shall I write like this? That means I want to consider S, I1, I0 as a single data. Okay, actually S is a one individual data, I is one individual data. I want to combine this one as a single data so that it's very easy for me to write the test bench. Okay, so that I'm able to take these vectors in the best way. So how do I do this one? I have S data, I have a I data. Okay, okay. I want to combine this one by using the concatenation operation. By using concatenation operation, I can combine these things. Right. S is a 1-bit data, I is a 2-bit data. I am combining these two as a single data. So what is the size of this single data? It is a 3-bit size, right? It's a 3-bit data. S is a 1-bit, I is a 2-bit, total 3 bits. So therefore, total 3 bits means I can write the entire table. So therefore, how do I write 0, 0, 0? This is the first case, right? So therefore, the first data is meant for, this is the first data is meant for S. This second 2 data are meant for I. Okay, first one the second data is middle one is I1, LSB is actually I0. Okay, so therefore after 10 nanoseconds, after 1 nanosecond or maybe 10 nanoseconds, for example 10 nanoseconds I'm using same data. What is the data? S comma I. What is the value of this one? 3-bit of 0, 0, 1. Okay, the second data is computed. Third data, for the third data, what I can do? Another 10 nanoseconds. S comma I will be 3-bit of 0, 1, 0. So third one is also completed. Okay, so I'll go for 10. S comma I is a 3-bit of 0, 1, 1. Fourth one is also completed. After another 10 nanoseconds, S comma I will be 3-bit of 1, 0, 0. This one is also completed. So after 10 nanoseconds, S comma I 3-bit of 1, 0, 1. Another 10 nanoseconds, S comma I 3-bit of 1, 1, 1, 1, 0 till last. Okay, another 10. So entire table must be required. Okay, so many alternative ways I told you in the previous classes. Okay, but for this particular case, only 3 signals, therefore I'm able to write this one. If suppose more than 3 signals, then I will go for another alternative. Okay, so that's what you have to remember. So finally, we need to end this one, end this test bench. No, it's not possible. Like this only we need to do. Okay. Okay. Finally, we need to write dollar monitor. Okay. So for that one, I need to start with initial. Okay, dollar monitor. So I want to monitor the things like time. I need to mention the time is equal percentage of t, and I need to mention yes, signal is a percentage of binary. Okay, so I is a percentage of binary only I want to look at, and y is also in the percentage of b only I look at that one. Okay, that's all. So finally, what is the first one I'm writing? What is the first one? First one is the time. Dollar time I need to write. Dollar time What is the second one? Yes. Third one is I. Fourth one is Y. So like this, I need to end this monitor statement. Finally, I need to, and the last but one is, I need to stop my simulation. Initial. Okay. When I need to stop my simulation, how much time it is required? So this is the 10, 20, 30, 40, 50, 60, 70. 70 nanoseconds. Therefore, I want to stop my simulation at 80 nanoseconds. Better we write another 10 nanoseconds to wait. Okay, and there we can start $stop or finish also we can write. Okay, finally we need to write and module. Okay, so this is how we need to write the test bench for the 2+1 multiplexer. So please remember that when you are realizing a circuit, by any means, it doesn't matter for the test bench. Okay, writing the test bench is similar for any implementation. Okay, so this is what we can say. So let us take another example. Okay, so let us write a Verilog program for 2x4 decoder. So please, can you please write the Verilog code for the gate level modeling for the 2x4 decoder? Write a Verilog program for 2x4 decoder using gate level modeling. Write a Verilog program for 2x4 decoder using gate level modeling. Okay. So I will give you the definition for this one. Okay. Next, we start here. So what is the 2x4 decoder is all about? Something like this. Having two input signals, for example, two input signals, something like this. It has got four output signals. Okay. But I'm interested to use writing in that vector notation. I'm interested to use in vector notation. So for that vector notation, I don't want to use these many lines. Okay. Just I will use only single line, but I should mention what is its size. Its size is 2. Similarly, I'll consider an output. What is its size? 4. 2x4 decoder. Okay. So therefore, the inputs are nothing but A. The output is Y, for example. Input is A, output is Y. Okay. Now, what is the inside of this block? Okay, since we are interested to write in gate level modeling, gate level circuit is required. Okay, so in a digital logic design course that we have seen, how do we design this 2x4 decoder? Okay, so first we have to take the truth table from the COM. Okay, so what is the truth table for this one? So A, I am writing in the vector notation means A of 1, and this is called A of 0. Okay, okay. Y means Y of 3, let us write. Y of 1, Y of 2, I'll write. Y of, so Y of 3, I need to write, sorry, Y of 1, I need to write. And Y of 0. So what is the functionality? What is the functionality? If 0, 0 is there, output is 0, 0, 0. If 0, 1 is the case, 0, 0, 0, 1. If 1, 0 is the case, 0, 0, 1, 0 is the 1. I'm sorry, this is actually this 0, 0, 1. This is 1, 0. This is 0, 0. This is the 1. What about last one? 1, 1 is there. 1, 0, 0, 0. Okay, so this is what. From this one, we need to write the Boolean equations for Y3. Okay, so therefore, what is the Y3 here now? Boolean equations. So what are the Boolean equations for Y3? Y3 is simply writing as Y3. If I want to write, I will write it as, for example, Y1 I will write first. So Y1, Y0 I will write. Y0. What is Y0 here? A1 complement A1 complement ila rastan complement. Next A0 complement. Okay, what about Y1? A1 complement A0, right? What about Y2? A of 1 A of 0 complement. Y of 3 ఏమవుతుంది? A of 1 A of 0. Okay, so these are the equations. From these equations I need to develop the mathematical equation, right? So what is the mathematical equation for this? Sorry, what is the logic diagram? I'll write logic diagram. So what is the logic diagram for this one? The logic diagram. I'll write this one. So better in this way people will write. Okay, so this is called A0. Sorry, A1. This is what we will write it as E of 0. Okay. Okay.
Sir, truth table opposite గా రాశారు సార్.
Truth table opposite గా రాసానా?
Yes sir. అది ఎన్కోడెడ్ సార్ మీరు రాసింది. డీకోడర్ డయాగ్నల్ గా జీరోస్ వస్తాయి సార్.
No, this is right only. Decoder output is right. You can check it.
Yes sir, నేను గూగుల్లో చెక్ చేశాను ఇప్పుడు మళ్ళీ.
2/4 decoder is right only. Yeah, how it will be wrong? So decode means when less number of inputs if you give, more number of outputs you will get it there. Okay. Okay, so in that case, if you have a 0 0 is the output, then the last one, only one output will be selected as only one output will be only one output will be highlighted, remaining all are zeros. So please check it once again, so it's right only. Okay, now
Yeah.
Next. Yes, we take one. Not is also required because in this implementation we need a not gate as well. Here also we need a not gate. Okay. Okay, so now we'll write one AND gate here. One AND gate is required, another AND gate is required, another AND gate is required, another AND gate is required. Okay. Okay, now, so this is the output. It is the output called y of 0. This is y of 1. This is y of 2. This is called y of 3. Okay. Now we take for y0 what is required? The complementation of a1, a0 is required. It takes the complementation part. Okay, so I'll consider this way. So this signal and this signal is required. Okay. Similarly, for this one, it is required. Sorry. For this one, it requires this one. 0 is required for this. 0 is required for this, but 1 is required from A0. Okay. Next, Y2. Y2 requires, what is the Y2 is required? Y2 requires that it must be the 1, but it must be logic 0. For this one, both are logic 1s only. So this is a logic 1. This is also logic 0. Please remember this way. Okay, so this is what the inside of your this is what the inside of your 2/4 decoder. Okay, so having 2 input signals, having 4 output signals. Okay, so we take this is a reference signal, reference 1, then we need to write a vanilla program for this one. Okay, so better I'll start with the programming here itself. Okay, so that it will be easy for me. So let us start. So why I'm writing these programs means it will be helpful to you to write difficult programs also. Okay, first you know the fundamentals very clearly, then only it is possible to write. Okay, for bigger problems. Okay, let us try. Let us write a module. It's 2 by 4 decoder. Decoder. Uh, dec underscore 2 by 4. So that's what I'm writing. A is my signal, Y is my signal. Okay, I want to mention the inputs are 2 down to 0 of, sorry, 1 down to 0 of A, and my output is 3 down to 0 of Y. Okay, so now as we know that we need to call the each and every gate. Okay, so better gates are also, I will write it in the form of blue, sorry, green color. So these gates I need to instantiate. Okay, so let us give the name of this gate is G1, G1, G2, G3, G4, G5, G6, right? Okay, so first let us write G1. Okay, what is the G1 here now? It is simply a NOT gate. Okay, NOT I will write. What is the name of the gate? G1. For the gates I will write the color G1, right? G1 है रास्ता. Next I will start. What is the output for G1? So do we have an output for the G1? Any name for the G1 is available? There is no G1 name is available. So better we need to write the name of this one is, for example, T1. Okay, T1. So I'll write T1 is my output. What is the input for this one? A of 1 directly it is coming. Okay, A of 1 is coming directly. Right. Next, what about another NOT gate? We have another NOT gate that is called G2. What is the name? Do we find any kind of name for this one? No. So let us write the name of this one is T2, for example. Okay. Now this is called T2. T2. This is called A of 0. Something like this. Next, we'll take another gate that is called an AND gate. And that is called G3 we are talking about. Okay, so what is the G3? Output is defined clearly by Y0, right? Y of 0 it is defined very clearly. What is the input for this one? T1 comma T2. Okay, next we'll write another AND gate. We write another AND gate G4 Y of 1. What about this one? It is required for G4. What is the input? One is A of 0. The next one is T1. Okay, we take another AND gate G5 Y of 2. ఇదేమవుతుంది T2 comma sorry. So ఇక్కడ ఏముంది మనకి one is A of 1 ఉంది. So I'll write A of 1. Next one is T2. Next I'll write another AND gate and G6. What is the value? Y of 3. ఇదేమవుతుంది బాబు? A of 1, A of 0. That's all. We need to write and module. That's all. What is the basic behind this one? Once we know the gate level circuit, then it is possible to write gate level modeling. Of course, we forgot to write whites because T1, T2 we need to write. So the whites are nothing but here also we can write white T1 comma T2. T1 comma T2 are the whites. Right. If you want to write it T1, T2 also in vector notation, you can also write 1 down to 0 of T. But you need to change inside of this one. Okay. So this is how we need to write a 2 by 4 decoder module. For example, I want to say once, of course, Verilog test bench also we can write it very quickly. So for the sake of simplicity, I'm writing the test bench only for the test vector positions only. Okay. So I will consider only these positions only I will consider. Okay. These positions only I'm going to consider. Okay. So the test bench, a part of the test bench I'm writing here. Test bench. So I'll start initial, begin. How do I start y? Okay. So what is the value? So I not I1 ఇక్కడ రాస్తాను. For example, ఇక్కడ మళ్ళీ again I'm repeating this one. E of 1, E of 0. So what are required? 0, 0, 0, 1, 1, 0, 1, 1. Okay. So simply I can write it's a 2-bit of, sorry. ఏమవుతున్నాయి A is equal to 2-bit of 0, 0. Simple as that. After 10 nanoseconds, for example, A is equal to 2-bit of 0, 1. After another 10 nanoseconds, A is equal to 2-bit of 1, 0. Okay. After another 10 nanoseconds, A is equal to 2-bit of 1, 1. Okay, na? That's it. The remaining things we can write it very easily. So this is how we can do. Or otherwise, I can say that A is equal to A plus B. Here, A is equal to A plus B is possible. Directly, we can write it. Only 1, 2 statements are sufficient for this one. But we have to use always block. Okay. So this is how we need to write. For example, a small modification I want to do. A small allocation. 2/4 decoder using enable input. With the 2/4 decoder with enable input and with enable input. So that means we have to include the enable signal for the 2/4 decoder. Okay. Most of the display icons are associated with some control signals. Okay. So depending upon the control signal, the inputs are taken into consideration or not will be justified. Okay. So in that situation, what I do, I'm going to consider a decoder something like this, having 2 input signals. Everybody knows that. Having 4 output signals. Okay, Y, A, but we are going to include an enable signal En. Enable signal is En. We are going to incorporate enable signal as well. So what is the truth table for this enable signal? That is right now. What is the truth table for this one? So we need to write enable signal first. A signal we need to write, and then Y signal we need to write. Okay. So if enable signal is equal to 0, irrespective of, I think I'll write it A1, A of 1, A of 0. Irrespective of any input signal it is, the function output is equal to Y of 3, Y of 2, Y of 1, Y of 0. Okay. It will be 0, 0, 0, 0. All are zeros. Irrespective of input output, it will be 0. If enable signal is equal to 1, then input has got some kind of value. If it is 0, 0, this value becomes 0, 0, 1. It will be the answer. Okay. For example, if 1, 0, 1 is the input. Therefore, 0, 0, 1, 0. If it is 1, 1, 0, if you apply 0, 1, 0, 0. If it is 1, if your inputs are 1, 1, 1, 0, 0 will be the output. Okay. So this is the what the output that we can have. So accordingly, Y of 3 can be defined, Y of 2 can be defined, Y of 1 can be defined, Y of naught is also will be defined. So what is the Y naught here now again? Y of 3, what is the, so Y of naught we will write first. Y naught L Rastamanam. So Y naught is defined by Y naught only the minterm is available here. Only this is the responsible pattern is sufficient. Okay. So for this one, we need to know that we have studied a lot about this one in our course. Enable signal E into A of 1 into A of 0. That means logical end operation among all these things. Oh, sorry, I want to write it as a complement of this one. Okay, so therefore now y of 1, what will be the y of 1? Y of 1 will be enable signal must be required. This is the pattern is responsible. So a of 1 is a complemented version is required, but a of 0 is as usual, we know that. So what about y of 1? What is the y of 1? Y of 2, sorry. It is actually enable signal a of 1, a of 0, total. Okay. Next, y of 3 is equal to, so this is the responsible one. Okay, enable a of 1 into a of 0. Okay, so if you compare with without enable signal, with enable signal means whatever we have derived previously, y0, y1, y2, y3 here, you see here. So whatever the things that we are deriving here, just we have to we have to include the enable signal. That's all. Okay, so if you compare this first equation, so this is the first equation. If you compare, for example, this is the first equation. Okay, copy and then I'll paste here. The compare, so I'm trying to just compare these two things. So without enable, we have nothing is there. Enable signal is not there. With enable, only this is included. Okay, please remember the point. So only this is included. So with this one, if dot bit enable energy. Okay, so that means instead of the 2 input AND gate for y0, we have to take 3 input AND gate. Okay, so therefore, what is the modification for this circuit diagram, logical diagram? What is the modification? I need to write one enable signal here and add the enable signal for each and every gate, and that becomes a 3 input AND gate, and we have to write 3 input AND gate related to this. Okay, and then we need to write a test bench for that one also. Okay, so for the everybody knows about description. Take it as a homework. And test bench part, the test bench, I'll write only for middle part only. Okay, so initial. Okay, let us begin here. Okay, so I know that I have a signal. I want to consider A signal and E signal as a single bit, not single bit, a single line. Okay, by using that one called enable signal E. Okay, sometimes I'm writing EN, no, but E I'm writing. So if you are writing the EN means EN only you have to write. If you are writing everywhere E, then you have to write E only. So don't forget about that one. Okay, I'm writing EN. So E I'm writing, for example. So this one I can write it. Okay, so this is similar to that of something like this. It's a 3-bit of 1 0. Okay, 1 0 0 is the first case. Okay, after 10 nanoseconds, for example, E comma AR 3-bit of 101. Okay, so here it is not necessary to develop the 8 combinations. Okay, not necessary. Why? Because it requires only this input combination only. Don't use space. I'm writing the spaces, but we should not write the spaces. So 0 1. So another 10 nanoseconds. E comma enable is equal to 3-bit of 110. The lastly, another 10 nanoseconds, enable is equal to 3-bit of 111. That's all. Oh, 2 times I need to write 0 1. Huh? Okay. So it also leather. We have only, this is called 1, this is 0, this is 1 0, this is 1 1. Okay, so this first bit is meant for enable signal. These 2 bits are meant for A signal. Okay, enable is required for all these things, but A is required 0 0 1 case, 0 0 0 0 1 1 0 1 1. I think you can understand this point. Okay, we'll write end module. So this is the part of the test bench I have written. you please copy this one and write a whole sum test bench for this. Okay, we stop it here today, and the remaining things we will see in the next class.